Perfect. Go ahead.
Well, as you saw earlier, thank you, Sarah, for the introduction, and good afternoon. Truly, thank you guys for having us present. We're very excited about this project. I do want to acknowledge my co-authors, Dr. Laura Norman and Barry Middleton with the Western Geographic Science Center, and Victoria Wesley, who's the forest manager for the San Carlos Tribe Forest Resources Program. Today, I'll speak about a project that we have partnering with the San Carlos Apache Tribe and supported by the Southwest Cask, as well as the Land Change Science Program, in which we're monitoring riparian vegetation response to fluctuating climate in order to inform restoration priorities within the Upper Gila River watershed. Let me see that. All right, here we go. I figured it out now. Sorry about that. So the Western Geographic Science Center has been working with the San Carlos Apache Tribe for a period of nearly 20 years, addressing a wide collection of resource management challenges, ranging from oak woodland habitats to wildfire and fuel treatments, and vegetation, land use, land cover change, among other topics. However, recent focus of the tribe has shifted to riparian vegetation that surrounds the waterways within the reservation boundary, which provide tremendous cultural and ecological value to the tribe. Paul Buck, who formerly worked for the tribe, approached us regarding the health of the riparian vegetation. The tribe has been interested in understanding the health of the riparian vegetation and addressing a need for fire breaks in future management, in addition to understanding how the overall ecosystem has changed over time in response to changing climate stimuli. Following these discussions, we collaborated with several programs at the tribe, including the Forest Resources Program, and proposed a study to the Southwest Cask to develop products that can be used to inform restoration priorities based on addressing concerns stated by the tribe and structured within a climate framework. Ultimately, we developed four primary research objectives. First, we hope to characterize historic vegetation and river channel properties of the riparian area. Second, we wanted to quantify recent trends in riparian vegetation conditions using satellite imagery. Third, we aim to identify the associated relationship between riparian vegetation dynamics and climate conditions. And finally, the core objective with this project, which is that we hope that these results would ultimately help the San Carlos Apache Tribe prioritize areas for restoration work. So our primary study site is the riparian zones within the San Carlos Apache Reservation. This includes the San Carlos River and the bilous reach of the Gila River, which both flow southwest into the San Carlos Reservoir. We also included a series of comparison study reaches upstream along portions of the Gila River, the San Francisco River, and Bonita Creek within the Upper Gila River Level 4 watershed. These sub-reaches allow for us to compare conditions within the reservation to conditions within the larger watershed. We wanted to focus specifically on the riparian vegetation zones surrounding each of these flow lines. So to do that, we isolated the riparian vegetation by digitizing a boundary around it, which specifically excluded both urban and active agriculture. These three sites that are shown here provide examples of the riparian zone along the San Carlos River, the left and the middle image, as well as the Gila River and the image on the right. So we use a series of indices in our scientific analysis to quantify drought conditions, as well as to monitor vegetation conditions over time. I list these indices here and include pictures on the left that visualize to some extent what they represent. So you'll see these pictures pop up next to the graphs that represent each of these data sources, and we'll go more in depth on each of these indices over the next few slides. However, I want to highlight the send slope trend analysis on the bottom. This was the approach that we used to calculate an estimate of the rate of change for each of the indices across our climate periods, which we use to assess changes in vegetation conditions and characterize the response to changing climate conditions. Our first objective was to characterize historic riparian vegetation and floodplain properties. These examples show some of the changes that have occurred between 1935 and 2019 on the reservation. Specifically, what you can see on these maps is there have been both large-scale shifts in the shape of the floodplain, as well as reductions in the width of the active flow channel. So in 1935, for example, the system was accustomed to large and widespread flows, resulting in a wide and structurally undefined active flow channel. In fact, in two of the examples shown here, we were not able to identify an active flow channel in 2019. So I think this does a really good job of highlighting some of the major shifts that have occurred during this 90-year period over time. Our second research objective was to address vegetation response within a climate framework. So to do that, we use the Standardized Precipitation Evapotranspiration Index, or SPEI drought metric, to monitor both wet and dry conditions throughout the watershed from 1980 through 2021. SPEI quantifies evaporative demand using precipitation and reference evapotranspiration as inputs, allowing for a robust representation of drought conditions. We use the breakpoint algorithm in our software, which identifies a break based on a shift in a seasonal pattern to determine when breaks occurred in the SPEI time series. Ultimately, the breakpoint algorithm identified two different breaks. the first in December 1993, and the second in September 2014. When we bookend these beginning and ending study dates, when we bookend these with our beginning and ending study dates of 1985 and 2021, we ultimately identified 3 separate climate periods. The first period runs from 1985 through 1993 and represents generally wet conditions. The second climate period runs from 1993 to 2014 and represents primarily dry and warm conditions, with SPEI values generally below 0 during this time. And finally, the third climate period runs from 2014 through 2021 and represents a period of intensifying drought conditions, with the most extreme drought conditions occurring at the end of our study period. At each breakpoint, we apply what we call a phenological framework in order to monitor vegetation conditions more in depth. So in this case, we define phenology as the natural shift in the timing of plant life in response to changing seasonality. So this framework can help us differentiate between various plant types within the riparian vegetation, specifically native and non-native vegetation species. So we included 4 different seasons, each covering 2 months. First, the spring season includes the months of March and April. The late spring season covers May and June, which is the hot and dry season across the southwestern United States. The summer season includes the months of July and August and represents the height of the wet monsoon season that we have. And then finally, we included the fall months of September and October to show seasonal decline in the vegetation. So to monitor the vegetation conditions over time, we use 4 different vegetation indices, including the Normalized Difference Vegetation Index, NDVI, as well as the tasseled cap transformation metrics of brightness, greenness, and wetness. So each of these indices can provide unique information on various aspects of the riparian vegetation. This GIF on the right shows yearly NDVI variability along the Gila River corridor, including the riparian vegetation, as well as the surrounding agriculture, which, as you can see as it lights up specifically over the word agriculture, does become much greener in general compared to riparian vegetation. So we produce 2 different multi-temporal raster products. First, we produce seasonal means for each vegetation index. This includes 1 image for each season per year from 1985 through 2021. And second, we produce climate period linear send slope products. So these products show this linear trend for each of the 3 climate periods for each vegetation index, and this was also done seasonally. So all of these raster products will be released as a formal data release in the USGS Science-Based Data Repository, which is hopefully coming out very soon, hopefully in the next week or so. So we chose to use a phenological framework in order to obtain more information on the vegetation types. Specifically, native cottonwood dominant deciduous gallery forest and non-native tamarisks typically have different seasonal signatures. So to both test and visualize this, we identified a series of points representing pure samples of these vegetation types using high-resolution imagery and extracted monthly values for each of the vegetation indices, with results for NDVI and tasseled cap greenness shown here on the left. So this image, which I found on Google Earth, which is an area located along the Gila River northwest of Pima, Arizona, shows the seasonal contrast that we hope to ultimately take advantage of. So for instance, during March of 2021, you can see that the cottonwood was beginning to green up, the cottonwood on the left, while the tamarisk vegetation remains senesced. So the phenology analysis shows that native deciduous gallery forest typically greens up at a greater rate in the early spring, particularly from February through April. An additional green up also occurs in the late summer monsoon season, following the seasonal rains and high surface water flows. On the other hand, non-native tamarisk typically greens up at a greater rate when compared to native vegetation in the late spring or early summer, or from May through June. This contrast in seasonality can help us better understand the native and non-native vegetation dynamics that may be taking place. So when reviewing general vegetation conditions along the primary study reaches, we can see that vegetation conditions were largely stable or increased slightly during the first climate period for our primary study reaches. So this is when conditions were wet. However, during the dry second climate period, NDVI widely increased. So in short, it got greener when it got drier. Now this was largely a result of flooding from the San Carlos Reservoir that had since receded, leaving that area to fill in with dense tamarisk. Across the third climate period, NDVI declined as a result of both drought and wildfire. So this decline was a little bit counterintuitive, as tamarisk typically thrives in dry conditions, but it does suggest that the fire and drought conditions that were occurring at that time may have had significant impacts on the overall vegetation condition, in addition to possible effects from the arrival of the tamarisk beetle, Diarabda, which occurred at the end of our study period. So when looking at upstream reaches along the Gila and San Francisco rivers, which have a much greater presence of native gallery forest, we see some very different patterns. So specifically, we see a continued green up in the summer and fall seasons throughout the third climate period when drought was intensifying. This seasonality suggests to us that native gallery forests are relatively healthy despite climate conditions in these areas. We're not sure what exactly was driving this response. Perhaps there was an increase in groundwater, or the vegetation may have been responding to increased carbon stocks, increased global temperatures, but it was very interesting and something that we hope to look at further in the future. So Barry Middleton, one of our co-authors, took this image last spring at the Gila Riparian Reserve along the Upper Gila River in New Mexico. I wanted to share it because I think it does a great job of highlighting truly how healthy and green this area was looking despite the drought conditions that were taking place. So overall, these forests were very healthy in the upper portion of the watershed. Now to rescale a little bit here. So we've been reviewing results at a watershed scale, but I wanted to transition a bit closer to the reservation boundary and focus on issues that can be used directly to inform restoration priorities for the tribe. So to do that, we developed a series of case studies that highlight locations that were identified during our discussions with our tribal partners and address concerns related to prior restoration applications, long-term impacts of resource management, and wildfire. For the first case study, we address a prior restoration application that was introduced to us multiple times, located at the confluence of Natural Crowell Creek and the San Carlos River. The restoration took place from 2006 to 2009 and had two primary objectives. First was to remove non-native tamarisk, and second, to use pole planting of cottonwoods to develop a native gallery forest in the region. Our research objective was primarily based on monitoring this phenological framework. So we were hoping to assess the efficacy of this restoration in meeting the two primary objectives. So for instance, would we see an increasing rate in spring NDVI, which would represent native gallery forest growth at this site? And would we see a decreasing rate in late spring season NDVI, which would represent a decline in non-native vegetation? So these photos that were taken by Paul Buck show the work that was completed at this site, including the removal of tamarisk on the left and the pole planting of cottonwoods along the flow channel on the right. So this just visualizes the restoration that took place. Overall, the region became greener during and following the restoration application. We first identified an increasing rate in spring NDVI during and following the restoration, particularly from February through April. So members of the tribe that we spoke to described this area as having a healthier, in quote, native deciduous gallery forest with numerous native species being present. Many of them provide very important cultural value. In addition, we also identified a decreasing rate in NDVI during the late spring season, specifically April through June. So this supports the conclusion that non-native vegetation is declining across the region and that the restoration objectives were met overall, which was really nice to see. So these are some additional photos from Paul Buck that show some of the long-term benefits of the restoration work, including cottonwood regrowth on the top left, an increase in vegetation species diversity, established wetland vegetation, and an increase in overall animal species diversity as well. Our second case study addresses a project that was completed by the Bureau of Indian Affairs during the 1960s and 70s, which is widely referred to as the Gila River Phreatophyte Project. This project has been widely documented in a series of reports by the USGS, which was involved in studying the land and hydrologic shifts as a result of this clearing. The overall objective of this project was to more effectively direct water through the floodplain by removing phreatophyte vegetation, using both mechanical-based methods, as shown in the images on the left from the Park et al. 1978 report, and chemical eradication using Silvex, which is similar in its chemical makeup to Agent Orange. Though these treatments primarily targeted tamarisk, which was the dominant species in the floodplain, other native phreatophyte species also present in the floodplain, including mesquite and cottonwood, were also targeted. Now, it's worth noting that this project had at the time a significant impact on the riparian vegetation of the area and has been described to us by a member of the tribe fittingly as a man-made disturbance. So to address the impact of this project on the current riparian vegetation, we apply what we call a mirrored subreach approach. So specifically, during this phreatophyte project, the floodplain was divided into a series of 5 study subreaches, ranging from subreach 0, upstream to the west, to the east, to subreach 3, the furthermost downstream subreach to the west. To simplify the impact of the treatments on the vegetation, we grouped these subreaches based on the amount of reservoir-induced surface water flooding from the San Carlos Reservoir and general vegetation properties, primarily density. So you can see the description of these subreach groups 1 through 4 on the map above, some with surface flooding and high density vegetation, and others with no surface flooding and low density vegetation. We also included a control subreach that was untreated, that does not experience surface flooding and has low density vegetation overall. So I wanted to show a series of aerial images that were collected by the USGS in 1973. So right now, this is just the present day imagery available in the ArcGIS base map product. And here's the 1973 imagery. So it's a bit hard to see, but these images show the scale of the clearing that took place along the floodplain, covering essentially the entire range of the riparian zones of the Gila and San Carlos rivers within the reservation boundary. Zooming in here, you can see a drastic transition that is present at the boundary of the reservation, where essentially all of the vegetation on the west side of the boundary was cleared, while the riparian vegetation remains intact east of the boundary. So overall, pre-existing conditions portray cycles of flooding-induced tamarisk invasion across portions of the treated subreaches, where flooding from the San Carlos Reservoir would result in loss of vegetation. When the flooding receded, the area would fill in with dense tamarisk vegetation. Following the phreatophyte treatments, downstream treated sites experienced only limited surface flooding and filled in with dense non-native vegetation when they were not flooded. Upstream treated locations that did not experience reservoir-induced flooding generally filled in with less dense non-native vegetation and even had some standing native vegetation. By the end of our study, the downstream sites appeared to show much higher levels of stress in the vegetation metrics, suggesting that these areas may be more vulnerable to climate impacts. On the other hand, the upstream treated sites showed less drought impacts overall, and I think it's possible that these upstream sites may even be more climate resilient based on the reduced level of stress during drought conditions. Nonetheless, direct impacts of the treatments are not fully understood and do require more study, such as species analysis or even a more detailed review of some of the spatially explicit vegetation regrowth patterns. However, reservoir-induced flooding or lack thereof during drought conditions appears to be the strongest driver of vegetation stress downstream. Our third case study addresses a growing concern among members of the tribe, which is riparian wildfire. So over the last 5 years, wildfire has become a much more significant and widespread issue within the riparian zones of the San Carlos Apache Reservation. So to address this concern, the development of fire breaks within the riparian zone has been introduced as a primary restoration and management objective for the tribe. To address wildfire in this study, we monitor both pre- and post-fire conditions by reviewing 2 fires which burned along the floodplain of the Gila River. The 2021 bottom fire, which burned roughly 6,000 acres between June 28th and August 18th of 2021, and the 2019 Bilas fire, which burned roughly 650 acres through portions of June and July of 2019. So here's a map showing the extent of these fires. The bottom fire was large and burned a substantial portion of the Bilas reach. And though the Bilas fire was much smaller in size, it did have some high severity fire associated with it. So we'll first address pre-fire conditions related to the 2021 bottom fire. So this fire had quite a large area that burned at high severity. So for instance, these photos were taken by Kurt Ehrenberg of the USGS Arizona Water Science Center, and they show the damage to a railroad bridge that crosses the Gila River, as well as a USGS gauging station along the Gila River at Calva. I think it's important to note that this level of damage on infrastructure, particularly to the gauging network, is unprecedented right there in riparian wildfire and highlights the threat that fires of this scale may pose in the future. Kurt did mention that in addition to this damage, 1 month of data was lost as a result. So if this had occurred during a flood event, this could lead to serious impacts downstream and overall highlights the risk of these large-scale fires. So these images will show direct impacts of the fire on the riparian vegetation. This first image is a pre-fire image from June 2019, about 2 years prior to the bottom fire. The second image is of the same area in 2021, about 6 months after the fire. So you can see a very large reduction in forest coverage across the full extent of the riparian vegetation zone. Also, in the high resolution imagery, we noticed a thin ribbon of vegetation located along the active channel that appears to have been, appears to not have been burned, or at least was not burned intensely. So this implies that there must be some threshold of either wetness or greenness that protects the vegetation from fire impacts, which is important to consider within a restoration regime. So once again, showing the pre-fire image and the post-fire image. So in looking at pre-fire conditions, we observed a series of both short and long-term changes in the bottom fire area. Specifically, we noticed declines in spring and late spring NDVI, greenness, and wetness between 2020 and 2021. So this is likely a representation of short-term degradation of the vegetation. We speculate that drought was the main driver for this, considering the climate conditions that were present during this time. However, though not formally documented, there is reason to believe that the tamarisk beetle may now be in this region for the first time, potentially adding to this decline. We also noticed a significant decline in greenness beginning in 2009 for all seasons except the spring. In the maps on the left, you can see this decline visualized. Greenness for 2008 is mapped on top, while greenness for 2009 is on the bottom. So despite this immediate decline that occurred within 1 year, conditions did remain relatively stable between 2009 and 2020 until we observed an additional decline, which was tied into the short-term degradation, which happened again in 2021. When addressing fire severity directly, we documented that higher severity occurred in areas showing greater pre-fire stress during the third climate period, as well as in greener areas within the locations of higher stress. So in short, we were seeing that stressed vegetation that was still green had been burning more severely during this fire. However, as I mentioned previously, vegetation in the immediate area surrounding the active flow channel was left primarily unburned. This was something that I think does need further study, certainly as we expand on potential restoration and the possible benefits that each method may be able to provide. Nonetheless, these fires are indicative of climate change impacts, and climate change is likely leading to increased fire hazards, even in riparian areas that are not historically prone to fires of this scale and magnitude. So I want to switch gears here a bit and look at a fire that allows us to review post-fire vegetation response. So this image is of the Byless fire boundary. You can see the impacts of the fire on the vegetation in the image, and now using a similar animation as before. This is a 2021 image from 2 years after the fire and does begin to show some revegetation occurring within the fire boundary. Now, seasonality certainly applies here, as this image was taken in late November, but we do see some revegetation response, possibly a precursor of recovery. So this graph shows the NDVI time series for 2014 through 2022, representing the length of the third climate period. We can see some contrasting conditions between the control site, which was to the southwest in blue, and a burn area in red. So first, the Byless burn area was generally greener and consisted of a greater density of forest vegetation than the control area. Now, this is important to note because it does appear that peak NDVI was declining in this Byless fire area prior to the fire. This aligns with our general conclusion that non-native vegetation condition was declining in this area because of drought during this time. Following the fire, initial recovery appears to be slow at first, but does begin to increase in 2021, though with a slightly different seasonality, and with greening up occurring later in the year when compared to the control site. So in summing all of this up, we do see revegetation occurring within the fire boundary area, though slowly and with a different seasonality. This may be a response to winter and spring drought conditions during this time, followed by intense monsoonal rainfall in both 2021 and 2022, which would drive some of this revegetation. Expanding on that, there are indications of possible state change occurring. Observations from our tribal employees suggest that the tamarisk is taking off in these burned areas. So any state change that is occurring is likely occurring in areas that were not previously dominated by tamarisk and maybe transitioning to that vegetation type. And I think this does beg the question, what species are climate adapted and can survive and develop following a wildfire? Is that tamarisk? And what does that mean for the native deciduous forests? I don't have an answer for that question for you today, but I do think it's something that does need to be considered as we see this expansion of intensive fire activity within our western riparian forests. So diving into some of the conclusions from this study, we identified that tamarisk is thriving because of the conditions that are present throughout much of this watershed, in which we have high amounts of sediment, high salinity, and limited surface water. Tamarisk was also shown to recover quickly and robustly following disturbances, both flood and fire. In general, however, tamarisk has also shown higher levels of stress during drought conditions compared to native species, particularly in areas that were no longer being flooded. These same areas experienced increased fire presence, severity, and long-term implications as a result. In general, native vegetation, such as cottonwoods, requires the presence of regular overbanking flows to propagate. So this can obviously be a challenge in arid land riparian systems, where surface water flows are often dependent on weather events and are susceptible to land management needs. However, future restoration plans could work to increase surface water on the small scale. One potential option is through the development of natural infrastructure in dryland streams, or NIDS. Some examples of NIDS are shown below, such as rock detention structures, beaver dam or beaver dam analogs, as well as willow hinge fells. Sorry, I pressed the wrong button. I've seen that slide before. Sorry about that. When reviewing some of the implications for restoration planning based on results of this remote sensing analysis, we identified a series of locations where restoration was shown to be effective and where it may be needed. One example of an area where restoration was shown to be highly effective is in the Natural Corral Creek area. Following the restoration, there has been development of native gallery forests, coupled with a decline in overall non-native vegetation coverage. So this has taken years to develop, over 10 years, but it does imply some of the implications for restoration in the future. So what are some of the areas that are showing degradation? One location is the lower San Carlos River, which has similar geologic and hydrologic properties as the downstream subreaches of greenness, even more extreme than what was observed along the Gila River. It has also experienced very extreme dense tamarask growth. If we were to compare this region to the same section of the Gila River, which had the large fire, the bottom fire, I think it would be fair to believe that this region along the lower San Carlos River may be at similar risk for wildfire. Additionally, post-fire vegetation response in the bottom fire may provide areas for restoration. The Bilas fire area is not fully revegetated 3 years after the fire. Many areas of the bottom fire had very high fire severity associated with it, in some cases removing all of the vegetation. So it's possible that there could be a positive impact for the riparian zone, and this may allow for a clean slate of restoration. Nevertheless, these post-burn sites serve as an opportunity for future restoration applications. When thinking beyond the Upper Gila River watershed, we were able to make several observations. Overall, when it dried out, vegetation filled in. So much of this likely occurred in former flooded areas and open channels, such as following floods along the San Carlos Reservoir. However, we also noticed an increase in native gallery forest greenness, even during drought and intensifying drought conditions, though this was more so in the Upper Gila River watershed and some of the primary tributaries. There was also a large increase in wildfire presence and scale over the last 5 years. Are these fires climate driven? Possibly. I think I would argue even likely. But what are some of the implications for native gallery forests that do not historically burn? This is occurring actively along the San Carlos River, where the native gallery forests have largely burned in the last few years. This could lead to significant transitions in vegetation structure and composition, and will be important to review in the coming years. When thinking forward, there are several directions that we hope to move in. Based on our discussions with tribal partners, the expansion of the tamarask beetle has become of great concern in recent years as it begins to move into this region for the first time, particularly related to fire impacts, as well as the endangered bird species that utilize tamarask as habitat. So we do hope to address this in the future. Additionally, we hope to improve our ability to identify and monitor tamarask vegetation condition in greater detail and in real time or even on demand with improved methods. These type of products could be extremely beneficial for the tribe in monitoring their tamarask forests and planning for restoration treatments. And finally, restoration plans on the reservation will include the use of natural-based solutions, or NIDS. For instance, members of the tribe joined with partners at Borderlands Restoration Network this past fall to participate in a workshop to train employees on watershed restoration techniques, including the sitting and construction of small rock and wood erosion control structures, native plant propagation techniques, and revegetation methods. So there's planning ongoing regarding the use of these structures, not only to restore the riparian vegetation, but also to reduce the risk for upstream floods. But on that note, I just wanted to quickly thank our funders, the Southwest Climate Adaptation Science Center and the Land Change Science Program. I want to thank our incredible co-investigators and partners on this project with the San Carlos Apache tribe. So thank you. And